Deep in the equations of physics lies a possibility so radical that it forces us to abandon everything we thought we knew about existence. What if the Big Bang wasn't the beginning? What if time stretches infinitely backward and infinitely forward, with no creation moment and no final death? What if the universe has always existed and always will, cycling through endless transformations that make our current cosmic epoch just one brief chapter in an eternal story? This idea doesn't just challenge cosmology. It threatens to overturn our most basic assumptions about causation, existence, and the nature of reality itself. Hit that like button and subscribe as we explore the most mind-bending model of cosmic existence ever conceived. Prepare yourselves. We begin. For nearly a century, the Big Bang has dominated our understanding of cosmic origins. The evidence seems overwhelming. Distant galaxies are racing away from us in all directions, suggesting that space itself is expanding. When we run this expansion backward, all of space converges to a single point approximately 13.8 billion years ago. The cosmic microwave background radiation, the faint afterglow of creation, provides a snapshot of the universe when it was only 380,000 years old, a hot, dense plasma filling all of space. The abundance of light elements like hydrogen and helium matches precisely what the Big Bang model predicts should have formed in the first few minutes of cosmic history. This evidence appears conclusive. The universe had a beginning. Time itself started at the Big Bang. Asking what came before is meaningless because there was no before. Before requires time, and time didn't exist until the universe began. This has been the standard cosmological picture for decades, accepted by virtually every physicist who studies the early universe. But the Big Bang model contains deep problems that have troubled cosmologists since its inception. The horizon problem asks how regions of space that were never in causal contact, that were too far apart for light signals to travel between them, ended up with identical properties. When we observe the cosmic microwave background from opposite sides of the sky, we see regions that should have been causally disconnected throughout the universe's history. Yet they have the same temperature to within 1 part in 100,000. How did they coordinate to reach thermal equilibrium if they could never communicate? The flatness problem is equally puzzling. The universe appears to be geometrically flat or extremely close to flat. Space doesn't curve back on itself like a sphere, and it doesn't curve outward like a saddle. It's balanced almost perfectly on the knife edge between these possibilities. This flatness requires incredibly precise fine-tuning of the initial conditions. If the universe's density had been even slightly higher or lower at the beginning, it would have quickly curved dramatically one way or the other. The fact that we observe near-perfect flatness billions of years later suggests the initial conditions were tuned to many decimal places. Why would the universe start with such special initial conditions? The singularity problem might be the most troubling of all. When we extrapolate the expanding universe backward to the Big Bang, the mathematics breaks down at a point of infinite density and infinite temperature. The singularity isn't just a place where our calculations become difficult. It's a place where the equations of general relativity fail completely, where space-time curvature becomes infinite, where the very concept of space and time ceases to have meaning. Physics cannot describe what happens at a singularity. The theory simply stops working. This singularity should bother us deeply. It suggests that our best theory of gravity and space-time is incomplete. General relativity is spectacularly successful at describing everything from planetary orbits to black holes to the large-scale structure of the universe. Yet when we apply it to the universe's origin, It produces mathematical nonsense. The theory tells us it cannot be trusted in precisely the regime where we most need it. Cosmic inflation was proposed to solve some of these problems. During the universe's first tiny fraction of a second, space expanded exponentially, doubling in size every 10 to the power of minus 35 seconds or so. This rapid expansion stretched a tiny region of space that was small enough to be in causal contact to a size larger than our current observable universe. That solves the horizon problem. Regions we see in opposite directions were once close enough to reach thermal equilibrium before inflation drove them apart. Inflation also solves the flatness problem. Any initial curvature gets stretched so flat by exponential expansion that the universe emerges from inflation incredibly close to perfectly flat. It's like inflating a balloon until its surface looks flat from your perspective. You don't need fine-tuned initial conditions because inflation creates flatness regardless of how the universe started. But inflation doesn't solve the singularity problem. In fact, it makes it worse. Inflation requires special initial conditions of its own. The inflaton field that drives exponential expansion must start in a particular state with particular energy density. Where did that state come from? And mathematical theorems proved by physicists including Alan Guth and Arvind Borde show that inflation cannot be past eternal. If you trace inflation backward in time, you still hit a boundary, a beginning, a point where space-time itself must have originated. This brings us back to the fundamental question. Why did the universe begin? What caused the Big Bang? Traditional physics has no answer. The usual rules of causation break down because causation requires time, and time began with the Big Bang. You cannot have a cause that precedes its effect if there is no time before the effect. The universe appears to be the ultimate causeless event, something that happened without anything making it happen. Many physicists find this deeply unsatisfying. The principle that every event has a cause has guided scientific thinking since the Enlightenment. Abandoning it for the universe's origin feels like giving up on explanation precisely where explanation matters most. Yet the mathematics seems to demand it. If time really began at the Big Bang, there cannot be a cause in any conventional sense. But what if time didn't begin? What if the Big Bang wasn't the beginning of time, but merely a transition, a moment when the universe changed from one state to another? What if time stretches infinitely backward, with no first moment, no creation event, no ultimate beginning? This possibility, though radical, resolves many of the problems that plague Big Bang cosmology, while introducing profound new questions about the nature of existence itself. The cyclic universe model proposes that the cosmos undergoes endless cycles of expansion and contraction, birth and death, stretching infinitely into the past and future. In this model, our current expansion phase, which began with what we call the Big Bang, was preceded by a contraction phase where space collapsed down to incredibly high density. At some critical point, quantum effects or other physics we don't fully understand cause the contraction to reverse, triggering a bounce into a new expansion phase. That bounce is what we observe as the Big Bang. Before our expansion phase came a previous universe, possibly with its own galaxies, stars, and planets. That universe expanded for billions or trillions of years, until dark energy or some other mechanism caused expansion to slow and reverse. The universe then contracted, growing denser and hotter as space collapsed inward. As this contraction approached the critical density, quantum gravity effects became important, preventing the formation of a true singularity. Instead of crushing to infinite density, the universe bounced, initiating the expansion we observe today. This cycle repeats eternally. each expansion phase is followed by contraction. Each contraction ends in a bounce that creates a new expansion. There was no first cycle because time extends infinitely backward. There will be no last cycle because time extends infinitely forward. The universe has always existed and always will, cycling through endless transformations. The cyclic model immediately resolves several Big Bang problems. The horizon problem disappears because regions we see in opposite directions were in contact during previous cycles. They had unlimited time to reach thermal equilibrium before our current expansion began. The flatness problem is solved because each bounce can reset the universe to near flatness regardless of how it ended the previous cycle. And the singularity problem is avoided because the universe never collapses to infinite density. It bounces before reaching that point. But the cyclic model faces formidable challenges. What mechanism reverses the collapse and triggers the bounce? General relativity alone cannot do this. Einstein's equations predict that gravitational collapse continues to a singularity. You need new physics, quantum gravity effects, or exotic matter with negative energy to make the bounce happen. We don't yet have a complete theory of quantum gravity that can definitively show such bounces occur. Loop quantum gravity, one approach to unifying quantum mechanics and general relativity, suggests that quantum effects naturally prevent singularities. In this framework, space is not infinitely divisible but made of discrete quantum units at the Planck scale. When the universe contracts to densities near the Planck density, about 10 to the power of 96 kilograms per cubic meter, quantum gravity effects become dominant. These effects create a kind of quantum pressure that resists further collapse and drives the bounce. Computer simulations using loop quantum gravity equations show that universes can indeed bounce. The contraction phase connects smoothly to the expansion phase through a brief period of quantum evolution, where classical notions of space and time break down. When the simulation emerges from this quantum regime, it describes an expanding universe very similar to what we observe after the Big Bang. The bounce replaces the singularity, providing a mechanism that keeps time flowing continuously through the transition. String theory offers another possible mechanism for bounces. In some string theory scenarios, the universe bounces when higher dimensional objects called branes collide in a higher dimensional space. Our four-dimensional universe might be a brane floating in a higher dimensional bulk. When branes collide, the impact creates matter and radiation that fills our three spatial dimensions, appearing to us as the Big Bang. After the collision, the branes separate, corresponding to our universe's expansion. Eventually, attractive forces pull the branes back together for another collision, creating a cyclic pattern. These theoretical frameworks are speculative and incomplete, but they demonstrate that the bounce mechanism is at least possible within extensions of known physics. The question is whether nature actually employs such mechanisms, or whether the universe really did begin at the Big Bang. One challenge for cyclic models involves entropy, the measure of disorder and information. The second law of thermodynamics states that entropy always increases. A cyclic universe should accumulate entropy cycle after cycle, becoming more disordered over time. Eventually, this entropy increase should drive the universe toward heat death, a state of maximum entropy where no further change is possible. How can the cycles continue forever if entropy keeps increasing? Some cyclic models address this by proposing that each bounce resets the universe's entropy to a low value. The quantum processes during the bounce might erase information and disorder, giving each new cycle a fresh start. This is speculative and controversial because it appears to violate the second law of thermodynamics. However, the second law might not apply during the extreme quantum gravity regime of the bounce, where our usual thermodynamic concepts break down. Other cyclic models embrace entropy increase and propose that each cycle is larger and longer than the previous one. The universe grows in size and duration with each cycle to accommodate the ever-increasing entropy. In these models, the cycles don't repeat identically. Each is bigger, longer, and more entropic than the last. This avoids the heat-death problem because the universe always has room to grow more disordered. Time still extends infinitely into the past, but the cycles get progressively smaller as you look backward in time. The conformal cyclic cosmology proposed by physicist Roger Penrose takes a different approach. Penrose suggests that the infinite future of one universe becomes the Big Bang of the next. This works through a mathematical trick involving conformal geometry, which preserves angles but not distances. In the far future, when the universe has expanded to near infinite size and all matter has decayed into photons, distance becomes meaningless. A universe of infinite size filled only with photons moving at light speed has the same conformal structure as the hot dense state at the Big Bang. Penrose proposes that these states are actually identical in the relevant sense. The end of one aeon, as he calls each cycle, is mathematically equivalent to the beginning of the next. The universe cycles through infinite aeons, each lasting trillions of years, with the ending of one providing the initial conditions for the next. Information might even pass between aeons in the form of gravitational wave signatures or other conformal invariants. Penrose claims to have found evidence of such signatures in the cosmic microwave background, though this remains highly controversial and contested by other cosmologists. All cyclic models face the challenge of observational evidence. Can we test whether the universe cycles rather than beginning at the Big Bang? Some predictions are possible. If the universe bounced from a previous contraction phase, that bounce might have left signatures in the cosmic microwave background, patterns or anomalies that differ from what pure inflation predicts. Researchers have searched for such signatures, but haven't found definitive evidence yet. Gravitational waves from the bounce might also be detectable. The violent process of the universe collapsing and rebounding should have generated gravitational waves throughout space. These primordial gravitational waves would have been stretched by cosmic expansion and might show up in gravitational wave detectors or in polarization patterns of the cosmic microwave background. Current observations haven't detected them, but future experiments with greater sensitivity might. The distribution of galaxies and large-scale structure also constrains cyclic models. The patterns we observe today originated from quantum fluctuations in the early universe. In cyclic models, these fluctuations might have different properties than in standard inflation, potentially leading to different predictions for how galaxies are distributed. Precise measurements of galaxy clustering and the cosmic microwave background can test these predictions. So far, observations haven't ruled out cyclic models, but they haven't confirmed them either. The data is consistent with both cyclic and Big Bang scenarios. This ambiguity frustrates attempts to determine which model correctly describes our universe. We might need observations of unprecedented precision, or we might need to wait for theoretical developments that make sharper predictions. Beyond cyclic models, other scenarios propose eternal universes without beginning or end. The steady-state theory, popular in the mid-20th century, before the cosmic microwave background was discovered, suggested that the universe has always existed in roughly its current form. As space expands and galaxies move apart, new matter continuously forms to fill the gaps, maintaining constant average density forever. This theory fell out of favor when the cosmic microwave background was discovered, because steady-state models cannot explain this relic radiation from a hot early phase. Modern variations on eternal universe models exist. Some propose that what we call the Big Bang was merely a local event in a much larger, possibly infinite, eternal space. Our observable universe began from a fluctuation or phase transition in this larger space, but the larger space itself has no beginning. This is similar to eternal inflation, where our universe is one bubble in an infinitely large inflating space that has existed eternally and will continue forever. Another approach suggests that time itself might be emergent rather than fundamental. In quantum gravity theories, particularly in approaches based on quantum cosmology, time might not exist at the deepest level of reality. Instead, time emerges from the correlations between different quantum subsystems. In this view, asking whether the universe had a beginning becomes ill-posed because time itself isn't fundamental. The universe exists in some timeless quantum state, and time emerges when we describe how different parts of that state relate to each other. This timeless perspective is philosophically radical. It suggests that past, present, and future all exist simultaneously at the fundamental level. The flow of time we experience is an illusion created by our limited perspective as observers embedded within the quantum state. The universe doesn't have a beginning or end in time, because time isn't fundamentally real. The entire history of the universe, from what we call the Big Bang to the far future, exists as a single timeless quantum object. This view finds mathematical support in the Wheeler-DeWitt equation, a proposed equation of quantum cosmology. The Wheeler-DeWitt equation describes the quantum state of the entire universe, and notably, it contains no time variable. Time disappears from the fundamental description, emerging only when you split the universe into subsystems and ask how one subsystem state correlates with another's. The universe as a whole doesn't evolve in time because there's no external time for it to evolve in. Time is internal to the universe, describing relationships between its parts. If this timeless view is correct, then questions about the universe's beginning become meaningless in a profound sense. The universe doesn't begin because beginning implies time, and time isn't fundamental. The Big Bang exists as part of the timeless quantum state, but it's not the first moment because there are no moments at the fundamental level. Past and future are equally real, all existing within the eternal, unchanging quantum state of the universe. This perspective resonates with some interpretations of Einstein's relativity, particularly the block universe view. Special relativity shows that simultaneity is relative. Different observers disagree about which events happen at the same time. This suggests that past, present, and future all exist equally, rather than the future being somehow less real than the present. The block universe is a four-dimensional structure containing all events throughout space-time, with the flow of time being a feature of conscious experience rather than objective reality. Combining the block universe with quantum mechanics leads to the timeless quantum universe, where even the block exists in superposition until observed. The universe is described by a quantum wave function spread across all possible space-time configurations. Our experience of time passing corresponds to our consciousness moving through one branch of this superposition, but all branches exist equally at the fundamental level. These ideas strain philosophical intuition to breaking point. We experience time as flowing, the present as unique and real, the past as fixed, and the future as open. Our entire conceptual framework for thinking about causation, change, and existence assumes that time is real and fundamental. Abandoning this assumption requires rebuilding our understanding of reality from the ground up. The eternal universe concept also connects to quantum mechanics' many worlds interpretation. In this interpretation, quantum measurements don't collapse the wave function to one outcome. Instead, the universe splits into multiple branches, with each possible outcome realized in a different branch. This splitting happens constantly throughout the universe as quantum events occur. The universal wave function never collapses and never began. It has always existed in a superposition of all possible universe configurations. In many worlds, cosmology, the Big Bang, might occur in our branch, but other branches might have different histories, perhaps including different Big Bangs or even no Big Bang at all. The multiverse of all branches has always existed and always will, with infinite variety across the branches. Some branches might be eternal in the sense that they have no beginning or end, while others might have finite lifespans. The totality, the full quantum state of everything, is eternal and unchanging, even though individual branches appear to change. This perspective makes questions about the universe's beginning branch dependent. In our branch, there appears to be a Big Bang, but the universal quantum state has no beginning. Which answer is correct depends on what you mean by the universe. If you mean our branch, it began. If you mean the full quantum state, it's eternal. The question's answer changes depending on your perspective. The philosophical implications of an eternal universe are staggering. If the universe has always existed, there was never a first cause, never an initial state that requires explanation. The chain of causation extends infinitely backward, with every event caused by previous events in an endless regression. This violates our intuition that explanation requires a starting point, a foundation on which everything rests. In an eternal universe, there is no foundation, just an infinite tower of causes and effects. This infinite regress troubles philosophers. How can we have an infinite sequence of causes? Doesn't explanation require that we eventually reach something uncaused, some necessary being or state that explains itself? Aquinas and other medieval philosophers argued for a first cause, identifying it with God, precisely to avoid infinite regress. An eternal universe brings the regress back, suggesting that reality has no ultimate explanation. Some philosophers embrace this. Perhaps reality simply is, without needing further explanation. The universe exists eternally, and asking why it exists is meaningless. Existence itself is the brute fact that cannot be explained. This position, called explanatory nihilism, accepts that not everything has an explanation. The universe's existence and eternal duration might be facts that admit no deeper justification. Others argue that infinite regress isn't actually problematic. Each event in an eternal universe is explained by previous events. The fact that this chain has no beginning doesn't mean events are unexplained. Every particular event has a cause, even if the totality of events doesn't. Demanding an explanation for the totality commits a fallacy, treating the infinite sequence as if it were a single thing requiring explanation. The debate becomes technical and abstract, but it matters profoundly for how we think about existence. If the universe is eternal, then existence has no explanation, no purpose, no ultimate ground. It simply is and has always been. Some find this liberating, others find it nihilistic. But the emotional reaction doesn't determine truth. The universe's nature is what it is regardless of how we feel about it. Testing whether the universe is eternal faces fundamental obstacles. We can only observe the universe from our current position in space and time. If time extends infinitely backward, we cannot observe that infinity. We see only a finite window, the light cone extending backward from our position to the edge of the observable universe. Events beyond our cosmic horizon are forever inaccessible. If the universe is eternal, most of its history lies beyond what we can ever observe. This creates a kind of cosmological limit on knowledge. We might develop perfect theories and infinitely precise measurements, yet still be unable to determine whether the universe had a beginning. The answer might lie outside the observable region, in epochs so far in the past that their light has not yet reached us and never will due to cosmic expansion. We could be forever uncertain about whether we live in a finite or eternal universe. Some argue this makes the question unscientific. If no observation can distinguish between finite and eternal models, then perhaps the distinction is philosophical rather than scientific. Science deals with testable predictions about observable phenomena. If eternal versus finite makes no observational difference, it's not a scientific question. Others counter that the question remains meaningful even if currently untestable. Past scientific questions were once beyond observation, but later became testable as technology improved. The composition of stars was thought unknowable until spectroscopy was invented. Perhaps future developments will let us probe earlier and earlier epochs, gradually pushing back the boundary of the observable. Or perhaps theoretical developments will reveal subtle differences between finite and eternal models that current theory misses. The eternal universe hypothesis also connects to anthropic reasoning. If the universe is infinite in time, then extremely improbable events become inevitable. Given infinite time, quantum fluctuations will eventually produce any possible configuration of matter, no matter how unlikely. This means that our existence, the formation of galaxies, stars, Earth, and life, requires no special explanation. It was bound to happen eventually given infinite time. This reasoning extends disturbingly. In an eternal universe with quantum fluctuations, you should expect to be a Boltzmann brain, a spontaneous fluctuation that briefly creates a conscious mind, complete with false memories of a coherent past. Boltzmann brains are vastly more common than real conscious beings like us, that evolved through billions of years of cosmic history. For every real observer, there should be infinitely many Boltzmann brains that merely hallucinate their experiences. If this is true, you should assign higher probability to being a Boltzmann brain than a real human. Your memories of reading this are probably false, generated by quantum fluctuation rather than actual history. This conclusion is absurd, suggesting something is wrong with the reasoning. Perhaps the universe isn't eternal after all, or perhaps the assumptions about how frequently Boltzmann brains form are incorrect. This Boltzmann brain problem plagues many eternal universe models. It's a reductio ad absurdum, suggesting that eternal time, combined with quantum fluctuations, predicts we should observe things we don't observe. This either rules out eternal models or indicates we don't understand the statistics of observers in infinite time. The problem remains unsolved and controversial. Despite these challenges, the eternal universe concept has profound appeal. It eliminates the need for a cosmic beginning, avoiding the singularity problem and the question of what caused the Big Bang. It makes the universe's existence more comprehensible by removing the mystery of creation from nothing. If the universe has always existed, we don't need to explain where it came from. The eternal universe also aligns with certain philosophical and religious traditions. Eastern philosophies often embrace cyclical time and eternal existence. Hinduism and Buddhism describe endless cycles of creation and destruction, with the universe perpetually transforming without ultimate beginning or end. The eternal universe models of modern cosmology resonate with these ancient intuitions about cosmic cycles. Even within Western thought, some philosophers have argued for eternal universes. Aristotle believed the cosmos was eternal, with no beginning or end. Spinoza's God was essentially identified with an eternal, infinite nature. While mainstream Western religion emphasizes creation and linear time, alternative philosophical traditions have always existed that embrace eternal existence. Modern physics might vindicate these ancient intuitions. The universe could be eternal in multiple senses simultaneously. Time might extend infinitely backward through endless cycles or bounces. The fundamental quantum state might be timeless, containing all moments at once. The multiverse of quantum branches might have no beginning or end. Each of these possibilities makes the universe eternal in a different way, and multiple might be true simultaneously. What would it mean for human existence if the universe is eternal? Some find the idea comforting. We're part of something infinite, something that has always existed and always will. Our lives might be temporary, but we participate in eternal cosmic processes. The atoms in our bodies have cycled through countless stars across potentially infinite time. We're temporary patterns in eternal matter and energy. Others find eternal existence disturbing. If the universe has no beginning or end, no ultimate purpose or destination, then existence seems arbitrary and meaningless. We're accidents in an eternal machine that grinds on forever without aim or goal. This nihilistic perspective sees eternal existence as robbing life of significance. But perhaps meaning doesn't require cosmic purpose. Perhaps the significance of conscious experience, love, beauty, discovery, remains even if the universe is eternal and purposeless. Our lives matter to us and to those we affect, regardless of whether the cosmos has ultimate meaning. Eternal existence might be neutral with respect to human values, neither supporting nor undermining what we find meaningful. The question of whether the universe is eternal ultimately comes down to the deepest issues in metaphysics. What is time? Is it fundamental or emergent? What does it mean for something to begin or end? Can existence have an explanation? Or is it the brute fact that grounds all other facts? These questions transcend physics, reaching into philosophy, theology, and the foundations of rational thought itself. We may never have definitive answers. The universe guards its deepest secrets well, hiding them behind horizons of observation and limits of theory. We see only a small window of cosmic history, from the edge of the observable universe to the present. What lies beyond, whether infinite past or timeless quantum state or eternal multiverse, might remain forever beyond our grasp. Yet the question itself is valuable. By asking whether the universe is eternal, we're forced to examine our assumptions about time, causation, and existence. We discover that reality might be far stranger than common sense suggests. Time might not be fundamental. Causation might extend infinitely backward. The universe might have no explanation beyond itself. The eternal universe challenges us to think bigger, to imagine possibilities beyond the familiar story of cosmic beginning and ending. It suggests that existence itself might be far more mysterious and magnificent than we imagined. Whether the universe had a beginning or has always existed, whether it will end or continue forever, we find ourselves in a cosmos of staggering scope and profound mystery. We are beings of finite lifespan, asking questions about infinity. We experience time flowing, yet we contemplate whether time might be illusion. We exist in the present, yet we reason about eternal past and future. This tension between our limited perspective and unlimited curiosity defines the human condition. We reach for understanding that might forever exceed our grasp. Perhaps that's enough. Perhaps the reaching matters more than the grasping. The eternal universe, whether real or hypothetical, serves to expand our minds and humble our certainties. It reminds us that reality is stranger and deeper than we know, that the foundations of existence remain mysterious despite centuries of scientific progress. What if the universe never started and never ends? We don't know. We might never know. But in asking, we touch something profound about the nature of reality and our place within it. The question itself, more than any answer, reveals our capacity for wonder and our refusal to accept easy explanations for the deepest mysteries of existence.